So today we're going to have two talks, and the first talk is given by Lai Guanwen from Massachusetts, and he's going to talk about on the irrationalities of modular spaces of K3 surfaces. So please.
Okay, thank you very much for giving me this opportunity to present my work. So this is a collaboration with Daniela Agostini and Ignacio Barros. So first, let me start with some basic definitions. So in this talk, by a polarized K3 surface, I mean a pair SL, where S is a complex K3 surface and L is a primitive ample divisor class on the K3S. Okay, and a polarized K3 surfaces of genus G, they form a 19-dimensional space. So in this talk, I will denote this space by Fg. They consist of pairs of SL, where the genus of L is equal to G. And we know from the degree genus formula, this is the same as this. So degree of L is the same as 2G minus 2. So in this talk, depending on the context, I may sometimes also use Fd, where D is 2G minus 2, which means the modular space of polarized K3 surfaces of degree D. Okay, so this is the motivating theory of our work. So this is proved by Gritsenko, Hulik, Sankaran in 2008. So they proved that the space Fg is of general type when G is greater than 62 and for a few values of G below 62. So in particular, we know Fg cannot be rational. It should be rational for this general. So this roughly tells you that when G is growing, when G is large enough, Fg is going to be irrational. So from the theory, we can ask a very natural question. How irrational is Fg as G grows? To answer this question, we need to make it rigorous about what it means by how irrational Fg is. So there are several measures of irrationalities right now in the society. So in this work, we consider two of them. So that X be a variety, usually assume it's irreducible. We consider the following two measures of irrationality. So the first one, introduced first by Mo and Henzer, is called degree of irrationality. So it's defined as the minimal degree delta of a rational covering from X to a projective space. So if X is a curve, then this is the same as the gonality of the curve X. So this is the second measure of irrationality we also consider, used recently by these 5 people. So this is called covering gonality. So it's defined as the minimal gonality of a curve passing through a general point X on the variety X. And we have the following facts about these two measures of irrationality. So first, from the definition, you can see they are birational invariants, and they also satisfy this inequality. So to see this inequality, it's not hard. So first, if you have a rational covering from X to a projective space, you fix a general point on X. This point gives you a point down below in the projective space. And then there's a line, pick a line passing through this point, pull back will give you a curve passing through a general point whose gonality is bounded by the degree of this rational covering. So in particular, covering gonality of a whole variety should be less or equal to its degree of irrationality. So this tells us that if we can estimate irrationality, if we can bound the degree of irrationality, then we'll also bound the covering gonality. And in fact, in this talk, in the remaining part of this talk, I will mention only degree of irrationality because although in the very beginning of this project, we consider both of them, but eventually we're able to estimate the degree of irrationality. Here, I just want to mention there are several measures about irrationality. Okay, so this is our main theory. For every epsilon real number which is positive, there's always a constant which C epsilon greater than 0, such that the degree of irrationality of the modular space of K3 surfaces of genus G is bounded by this constant times G to the 14 plus epsilon. So this tells you that in particular, the growing of the irrationality depending on G is like it grows polynomially. Okay, and in some spatial cases, so in some spatial G or equivalency for some spatial degree D's, we can refine this estimate as follows. Okay, we can improve this estimate to C times G to a 10th power instead of 14 plus epsilon in the following three families of D's. Okay, here D is the degree 2G minus 2. So the first family is this. So it's when D is congruent to 0 or 2 modulo 6, and is not divisible by 4, 9, or any other prime P, congruent to 2 modulo 3. And the second family is this. So second family consists of the degrees, which are congruent to 2, 4, modulo 8, which is not divisible by any prime P, congruent to 3 modulo 4. And the third family actually consists of infinite many families. So there are the D's such that 1 D over 2 minus some integer, positive integer n is a square. So in the following, I'm going to talk about discuss the details about this case. So this is actually the initial how our project starts. So we first started this family, and for the other two, the construction, the proof will just be parallel to this one. And in the end, I will go back to talk about the uniform estimate of both, the most general one. Okay, so all of the ideas will be contained in this first case. Okay, so let me enter the details about the first case. So the first case, the degrees of the K3, so the K3 surfaces with degree in the first family, they have associated cubic fourfolds. So I need to remind you what, I need to give you some brief introduction about cubic fourfolds. Okay, so by cubic fourfold, I mean a cubic hypersurface in P5. And in the following, I will denote by H the class of the hyperplane section. Okay, so we know for a very general X, it's H22, right? In the middle cohomology, is generated by H squared. Okay, or in other words, every algebraic surface in X is homologous to a complete intersection. And we say cubic fourfold is special if it contains an algebraic surface not homologous to a complete intersection. Or in other words, this means that H22 contains some rank 2 sublattice, which is saturated and contains H squared. And for such kind of sublattice K, we'll call it a labeling. Okay, so X is special if it contains a labeling. And given a labeling, we can define its discriminant. So it's simply the discriminant of it as a lattice. Okay, or it's the determinant of this matrix, the determinant of this matrix formed by intersections of its two generators. Okay, and so what do we mean by associated K3 surfaces or associated cubic fourfolds? So now, suppose we are given a special cubic fourfold carrying a labeling of discriminant D. And suppose we also have a polarized K3 surface of degree D. And we say, okay, so as abstract lattices, we always have the following isomorphism. So on the left-hand side, this is the orthogonal complement of K, the labeling inside the middle cohomology of X, twisted by -1. So this will be isometric to the orthogonal complement of the polarization L inside middle cohomology of the K3 surface. So they're isometric abstractly as lattice because they both are isomorphic to this guy. So now it's Z. So the first one is a rank 1 lattice generated by a vector with self-intersection minus D. The middle consists of 2 copies of the hyperbolic lattice, 0, 1, 1, 0. And the last one consists of 2 copies of EA lattice twisted by minus 1. And we say the labeled spatial cubic fourfold and the polarized K3 surface are associated if there's an isomorphism like this, which also preserve the Hodge structures. So these 2 lattices, they carry their own Hodge structures. We say they're associated if there's such kind of isometry preserving also the Hodge structure. Okay, and so I need to talk about moduli space of spatial cubic fourfolds. So first, the moduli space of cubic fourfolds form a 20-dimensional space, which is the quotient, this quotient. Okay, it's the quotient of the systems of cubics. You collect all that are smooth, quotient by the PGL 6 action. And spatial cubic fourfolds, which carries the labeling of discriminant D, or briefly, spatial cubic fourfolds of discriminant D, they form this 19-dimensional locus. It's a no-third left stress locus. It consists of cubic fourfold containing a labeling of discriminant D. So it's proved by Hassett that every such CD is an irreducible divisor, and it's non-empty if and only if D is greater or equal to 8 and congruent to 0, 2, module 6. So here are some examples. Like this list starts from 8, 12, 14, 18, 20, and etc. Here are some examples. And so some of these CDs, they are related to K3 services in this way. So we say a member inside the CD, suppose it's non-empty, and admits an associated K3 service if and only if D is admissible, which means that D is, so first you want CD to be non-empty, so it must be in the list given in the previous slide. And you also need to satisfy this property. D is not divisible by 4, 9, or any other prime P congruent to module 3. So here are some examples. So this is a list, the same as in the previous slide. Here I highlight those which are admissible. Okay, so there are 14, 26, 38, and then 42. So these are 4 examples where a member in CD, a cubic fourfold in CD, has an associated K3 surface. And again, this is given by Hassett. So for each admissible D as above, there exists a finite dominant rational map from FD to CD, okay, which is birational if D is congruent to 2 module 6 and of degree 2 if D is congruent to 0 module 6. So in other words, if D is congruent to 2 module 6, every such general cubic fourfold in CD, it has one associated K3 surface. And if D is congruent 0 module 2, module 6, then a general member in CD has 2 distinct associated K3 surfaces. Okay, and from this finite dominant rational map, we can get the following inequality. So for each admissible D, the degree of irrationality of the moduli space of K3 of degree D is less or equal to 2 times the degree of irrationality of the moduli space of discriminant D cubic fourfolds. Okay, so this turns the problem about estimating the degrees of irrationality of the moduli spaces of K3 surfaces to problem about estimating the irrationality of moduli spaces of cubic fourfolds. Okay, so starting from next slide, we are going to estimate the degree of irrationality of those CDs. Okay, so how do we treat such estimation? So it turns out that those CDs appear as components of the so-called Hignar divisors. Okay, so I'm going to use this slide to introduce some basic notations that I'm going to use later. First, in this talk, I'm going to use N to denote a lattice. And lattice in this talk will be signature N2, where N is assumed to be even. And in the following, we'll also consider the discriminant group. Okay, we'll denote it by D of N, which is the quotient of the dual lattice quotient by N. And for dual lattice, you can consider it as the vectors in the lattice, original lattice over Q, whose pairing with the element in the original lattice are all integers. And we'll also consider this monodromic group. They are the automorphisms on the lattice which acts trivially on the discriminant group. We'll also consider this period domain, we're denoted by omega n. It's a quadric, is a quadric in this projective space, a projectivization of M over C. And we'll also consider this period space denoted by Pn. It's a quotient of period domain by the monodromic group. Okay, these are the notations we're going to use. Okay, so let me keep these two guys. And this is the definition, and it's also a theory. It's proved by Borchardt in 1999. So if you fix a positive rational number and also a positive rational number n and an element in a discriminant group, then you can define this union of hyperplane sections. Yeah, so this is the thing yn gamma tilde. This is a union of hyperplane sections on the period domain omega. They are the orthogonal complements of the vectors v. V is taken from the dual lattice, which satisfy the two numerical properties there. Okay, so we require the self-intersection of v divided by 2 is equal to the chosen rational number n. And we also require the class of v in the discriminant group is the same as the chosen element gamma. And it's proved by Borchardt that this union, it descends to a Cartier divisor on the period space. And this is called the Hignar, there's a typo, Hignar divisor. Okay, so this is the definition of Hignar divisor. Okay, so now let's return to the case of spatial cubic fourfolds. So first of all, let me review the periods about spatial cubic fourfolds because I need notation. So let X again be a cubic fourfold, and consider that in this case that N to be a primitive lattice in a middle cohomology. So it's an orthogonal complement of the H square, and it's abstractly isomorphic to A2, some with 2 copies of the hyperbolic lattice, some with 2 copies of the EA lattice. So you can see this guy has signature 22. Okay, so here N is 20. And we can define this. So this is supposed to be a lift of the periods of the spatial cubic fourfolds of discriminant D. Okay, so this CD prime tilde is defined as this union of some sections. Okay, so K, you run this, we take the orthogonal complement of all of the labelings in the middle cohomology of X, and we consider orthogonal complement on the period space, on period domain. So here I want you to notice that here period domain, it lives in the projectivization of N tensor C, which means that it's in this space. But remember, labeling, it's a rank 2 saturated sublattice in the middle cohomology in H4, which contains H squared. So these sections, these orthogonal complements, they are actually hyperplane sections on this period space, on this period domain. And it's famous theorem that Touré theorem for cubic fourfolds, proved by Basson, and later there are some details given by Laza, that the modular space of cubic fourfolds of discriminant D admits an open immersion into this quotient, okay, the quotient of the CD prime tilde above by the monodromy group on this PN. Yeah, we have this open immersion. So in particular, this tells us if we want to estimate the degree of irrationality of CD, it's the same as estimating the degree of irrationality of this CD primes. Okay, so also notice that, yeah, I'm going to use this in the next slide. The discriminant group of the lattice M in this case, it will be the same as the discriminant group of A2. So above you can see M consists of A2 and U and EA, they are all unimodular. So discriminant group of the same as A2, where A2 is given by this 2 minus 1 minus 1, 2. So this is the same abstractly isomorphic to this group Z mod 3Z. Okay, so here's a lemma proved by Li Zhiyuan and Zhang Letao in 2013. So if we denote by gamma 1 a generator for the discriminant group, then we will have the following relation. So CD prime will be a component of this Hignar divisor, y d over 2 and gamma, where gamma will be the 0 element in the discriminant group if d is congruent to 0 modulo 6, and gamma 1, gamma will be the same as gamma 1, the generator, if d is congruent to 2 modulo 6. And here, let me give you some idea about how to see this inclusion. So this can be verified by comparing their lifts on the period domain, okay, on period domain omega n. So remember, in the previous slides, we have a definition for the lift CD prime tilde, which is this union of orthogonal complements of labeling K. And on the right-hand side, the lift is defined as the union of orthogonal complements of vector B, which are taken from the dual of the primitive lattice, which satisfy these two numerical conditions. So to prove the inclusion, you only need to prove that you take one labeling from the left-hand side, and then you compute its orthogonal complement in the primitive lattice. So this is a hyperplane in a primitive lattice. So the only thing you need to do is to find another vector whose orthogonal complement is this hyperplane section. Okay, so the idea is quite simple, and this can be computed very explicitly, and then it will give you the above result. So in particular, to estimate the degree of irrationality of CD prime, this problem turns to the problem about estimating of the degree of irrationality of these Hignar divisors. Yeah, so remember in the like 10 minutes ago, I said so remember we are talking about the estimate about the degree of irrationality of moduli space of K3. And then this turns to a problem about estimating the degree of irrationality of CD. Okay, they are the moduli space of spatial cubic furfels. And this turned to the estimate about the degree of irrationality of this CD prime the periods. And now this turned problem further to estimate about degree of irrationality of these Hignar divisors. Okay, so how do we estimate the irrationality of these Hignar divisors? It turns out that these Hignar divisors form some kind of modular forms. So I need to recall some definition and also introduce some notations I'm going to use about modular forms. So now remember, in the following, I will denote by H the upper half plane in the complex plane C, and we'll also consider the usual action of the modular group, okay, which modular group is SL2Z, which acts on the upper half plane in the following well-known method. Okay, and also recall that the modular group is generated by these two elements. S is the inverse, so acting on the upper half plane, it's act by taking the inverse, taking the minus of the reciprocal, and T is the translation by 1. And I also I'll also need this notation. So the congruent subgroup gamma n of level n inside the modular group gamma is defined as the kernel of this sequence. Okay, the kernel of the map from gamma SL2Z to SL2Z with coefficient in this cyclic group Z mod NZ. So these are some notations. Okay, so also remember a modular form of weight k where k is an integer for gamma n is a holomorphic function on the upper half plane that satisfies this transformation rule. Okay, and the transformation rule, if you plug in G equals translation by n, okay, T to n is translation by n, it will give you this equation. Yeah, it tells you that the modular form is periodic with period n. So in a meta Fourier series expansion like this. Okay, so here it's a sum of some coefficient Cn times q to the n over n. Here q is e to the 2 by I tau. Okay, and this is a key effect we are going to use in our estimate, and we believe this is a general and this is well known. So suppose that k is greater or equal to 3, then the coefficients of the Fourier series expansion above satisfy this estimate. It's bounded by some constant c times n to the k minus 1's power. So to see this fact, this follows mainly from another fact that such kind of modular form is always a sum of a cusp form and an Eisenstein series. And we have a bunch of estimates about these two very classical forms. Okay, so this basically follows from this fact. Okay, but in this work, we also need vector valued modular forms. So let V be a finite dimensional vector space over C, and let's fix some representation of the modular group gamma on V, and suppose that it acts trivially on the congruent subgroup gamma n for some n. A modular form of weight k of type rho this is a vector valued modular form. Is a holomorphic function from on upper half plane with value in the vector space. It satisfies the similar transformation rule. The only difference from the scalar case is that there is a action of the representation in the middle, the rho g there. And due to our assumption, our representation, you can also verify this simple equation here. It's periodic with period n because we have the transformation rule. You can verify it by transformation rule with g replaced by substituted by translation by n. And this is also and also the fact that the assumption our representation acts trivially on a congruent subgroup. So we can use this fact to verify this equation. So in this case, we still have a similar expansion as above, as a previous scalar case. So if you fix the basis eigenvectors for this matrix, okay, rho t, rho evaluate on the translation generator, then there's a Fourier series expansion of the modular form in this way. So it's an expansion with respect to this basis, and the coefficients of the in front of each of the basis element itself is a scalar modular form, and it's of weight k for the congruent subgroup gamma n. So they are the scalar modular form that satisfy the fact that I mentioned before. So we have this immediate correlate. Okay, suppose again k is greater or equal to 3, then the coefficients of these modular forms here, they are all bounded by some constant times n to the power k minus 1. Okay, and Higner divisors, it turned out these Higner divisors form some kind of vector valued modular forms. So recall that n we denote by m a lattice of signature m2 where m is even, and we'll also consider the group algebra of its discriminant group. So in this case, to form modular form, this is going to be our vector space, in the vector space V. So our modular form will take value in this space. And in this space, we'll denote by V gamma, the element corresponding to gamma in the discriminant group. Okay, then there's a representation from modular group gamma, which is SL2Z, to the group algebra of the discriminant group, which is defined in this way. So we know the modular group is generated by S and T, so it's sufficient to define, if you want to define representations, it's sufficient to define how they act when evaluating at these two generators. So they act in this way. So in particular, like for example, the representation at the T translation act on the basis elements as like their eigenvectors, and it act on S, evaluate S act on the vectors in a more complicated way. Okay, so anyway, we have this representation. And then we have this result due to Borchardt in 1999, and then by McGraw in 2003. So the generating series with coefficients, so here we have a generating series with coefficients considered as elements in the Picard group of the period space. Okay, so this is a generating series of those Higner divisors. Now you sum over Higner divisors times q to the n. The n come with the n of the Higner divisors, and then sum with V gamma, where gamma runs over the elements in the discriminant group Dn. So they proved that this is the factor valued modular form with coefficients in Picard group of weight 1 plus n over 2 and type rho m. So rho m is like the representation defined in the previous slide. And in the case of special cubic flow, remember our n is 20. So in our case, this modular form is going to be of weight 1 plus 20 over 2, which is weight 11. Okay. And here's another also important and also classical and also well-known result due to Brady-Borel. So the period space is a quasi-project variety, which admits a normal compactification such that the boundary has codimension at least 2. Okay, so using these two facts, I'm going to show Higner divisors. I'm going to estimate the irrationality of Higner divisor. So the theorem by Brady-Borel tells you the following. Okay, there are some consequences. So it tells you that the divisor class group on Pn and its compactification are isomorphic. So this allows us to, for example, first, this space is projective, so you can fix any embedding into a projective space. Okay, fix any embedding of a Brady-Borel compactification into some projective space, and then this induces a homomorphism. Yeah, it's a degree function, so you can talk about degrees of elements in a divisor class group in Pn in a good way. Okay, it's well defined. So this function, this homomorphism, is defined by taking divisor to the degree of its compactification in this chosen projective space. Okay, we can talk about degree this way. So by evaluating this degree function at the generating function of Higner divisors in the previous slide, you get the following generating series, with now their coefficients are all integers. Okay, so this is an evaluation of this degree function of at the previous generating function. So of course, it's because the original generating series is a modular form of this weight and this type. This thing will be kept for this guy. The only difference is its coefficients are integers. And now we are able to prove this irrationality, this estimate about irrationality of Higner divisors. So let n be a lattice of signature n2, but we assume n to be greater or equal to 4. Okay, and here n in our case are all assumed to be even. And suppose yn gamma prime is an irreducible divisor of the Ignar divisor. Then we have this estimate. So its degree of irrationality will be bounded by some constant times n to the m over 2 for some constant c. Okay, so again, in our case, for special cubic fourfold, and also for the K3 surfaces of degree in the first family, our m is 20, so n, like the power here will be n to a 10, as described in the theory. Okay, so how do we prove this theorem? This follows basically by collecting the information given in the previous slides. So first, again, we choose an embedding of the Bailey-Borel compactification of yn gamma in some projected space. And so if we project the component, okay, so we'll also compactify this component in this project space. We choose some general linear projection. This will give you a dominant finite finite morphism to a projected space, the finite covering. Its degree will be at most the degree of the Ignar divisor, which the degree of Ignar divisor that carries this component. And so in particular, this because of the existence of this rational covering, the degree of irrationality will be less or equal to the degree of this kind. And so we also have the estimate given in previous slides about modular forms that this degrees grows in a way given in a theory. So combine all these inequalities together, you'll get the bound about the degree of irrationality. Okay, so this is the sketch of the proof. So this basically finished the case, the first case about how we estimate the growing of the degree of irrationality of moduli of K3. Okay, so let's return to our main theory. Okay, so I basically finished the discussion about this case. Yeah, so so when D is congruent to 0 or to modulo 6, not divisible by 4, 9, or any other prime P congruent to 2 modulo 3. Okay, so this case basically follows from the fact that we have associated spatial cubic fourfold. And remember, the problem is this estimate can be done because we can turn the problem into the estimate of modular space of this spatial cubic fourfold, and then to a problem about Ignar divisors. And for the second family, the estimate is basically, so the estimating process is basically parallel to the first case. So in this case, the main thing that are related, that are used here is the spatial Gushio-Mukai fourfolds. And this whole theory about associated spatial cubic associated K3 surfaces of this Gushio-Mukai fourfolds. It's established by these three people, Debab, Elif, Manival in 2015. And for the third case, it's now in the third case, what we use are spatial hyperkähler fourfolds. Okay, so there are some hyperkähler fourfolds of K3 type, and the theory about associated K3 to this space, to this hyperkähler fourfolds are developed by Debab and Macri in 2019. Okay, so so now the three cases, the argument in the three cases are all parallel to each other. Okay, so in the remaining part of this talk, I'm going to talk about the uniform estimate. But I guess before I keep going, I should pause to see if there's any questions so far. So is there any question?
Yeah, I think it's clear enough so far.
Okay, good. So just let me keep going and let me drink some water. Okay, so the last is uniform estimate. Basically, follow the same. This estimate follow similar idea as the three cases here. But instead of Higner divisors, the thing involved in this uniform estimate are the so-called Kudlas cycles. Okay, so there are these cycles from some kind of modular forms. They form the so-called Siegel modular forms. So again, I need to set up some notations here. So consider this Siegel upper half space. Okay, they are the space. This is the space consisting of R by R symmetric matrix, such that the imaginary part is positive definite. Okay, so each tau is a matrix, and we have this action of the symplectic group on this Siegel upper half space, which act in a quite similar way as a scalar modular form case. But the only thing you need to be careful about is because we are working with matrices, so we need to be careful about the order, for example, the product of order product here, and let V be a complex vector space and also fix some representation rho of this group gamma n on V, and also suppose it's trivial on some congruent subgroup. Then a Siegel modular form of genus R with K and type rho is a holomorphic function vector valued on the Siegel upper half space that satisfies this transformation rule, which is quite similar as all of the previous cases. Okay, and such similar to the scalar and vector case, such kind of modular form meets also a Fourier series expansion, but it's more complicated here in a way that this summation here is indexed by symmetric. I think I missed some notation there. Symmetric R by R matrix with entries in rational numbers, and they are which are semi-positive definite. Okay, so here T in particular is a matrix, and Q to T is not just the power. It's this guy. It's E to 2 by I times the trace of the matrix formed by multiplying T and the matrix tau. Okay, so it's more complicated here. And again, we have some fact about the growth of its coefficients. So we believe this fact is probably well known to experts in this area. And we found this fact from the book written down by these two people. Okay, we don't know if these two people are the original creator of this fact, but we found it in a book written down by these two people. So there exists a constant C such that the coefficients in this Fourier series expansion is bounded by C times the determinant of T to a K's power. Okay, so remember K is the weight. Yeah, so this is enough for us to do our estimation. So as I mentioned, in the general case, we use Kudla's spatial cycles instead of Wigner divisors. So what are Kudla's spatial cycles? So again, let M be a lattice of signature M2. And again, suppose M is even, and let all of these notations be the same as before. Okay, so omega M is the period space, is the period domain, PM is the period space. And now let's fix an R tuple V consisting of V1 to VR. So V1 to VR, each VI, they are vectors in the dual lattice of M. Okay, it's an R tuple. Each such kind of R tuple, they determine a linear subspace in the in M span in M over Q. Okay, so it's determine its span. And it also determines a so-called moment matrix. So it's a matrix whose entry is 1/2 of its ij entry is the product of Vi and Vj. And now you need to take 1/2. So this is called moment matrix. Okay, again, we have this theorem which is quite similar to the Higner divisor case, but this is due to Kudla. So for each, if you fix an R by R symmetric matrix T in centers in Q, which is semi-positive definite, and also fix an element and R tuple in the like R copies of discriminant group. So in this case, this like both face R gamma is an R tuple of elements in the discriminant group. And given this T and this gamma, we can define this union D T gamma tilde. So it's the union of the orthogonal complement of the span of the linear space determined by V, R tuple V, where V satisfies the two numerical properties there. First, you want the moment matrix of this V is the same as the T that you choose in the beginning. And you also want its class in the R copies of discriminant group is the same as the chosen gamma above. Where you run over such orthogonal complements, and then this guy will descend to a cycle on the period space. So originally, this orthogonal complement are taken in a period domain omega. Now it descends to a cycle to a cycle below in the period space, and this cycle's dimension will be equal to the rank of the matrix T that you choose in the beginning. Yeah, so this is called Gould cycle. And these cycles, so about these cycles, so they form a generating series. So first, that's denoted by the restriction of O1 on the perturbation of M over C to the period domain is invariant under the modular group action. So it descends to a line bundle L on the period space. Okay, so that's using this, now we can define a generating series. So in this generating series, the coefficients is a product between the Gould cycle and the first class of this line bundle. And you multiply it with the first class of line bundle. One of the purpose here is you want these coefficients to have the correct codimension. Okay, yeah. So remember, the Gould cycle has codimension the same as the rank of T, and so we need to multiply with something to make it the coefficients to be cycles in child group of codimension R. Okay, so and this summation runs over all the symmetric matrix T, which is semi-positive definite in rational numbers. And now we have the theorem. So Zhang and Bunier, Westerholt, Run, these three guys, they proved that this generating series above it form a single modular form of genus R and weight 1 plus m over 2 under a certain representation. So this representation here is quite similar to the case of Higgs divisors, but of course it looks more complicated, so I don't want to write it down here. Okay, so they proved that this generating series is a modular form. So in particular, if you evaluate this generating series by some linear map on the child group, then you will still get the modular form. And this is the modular form that we want. So later on, this linear map here will again be some kind of degree function. Okay, so we have this series, which is a modular form. And next, so about the irrationality of these spatial cycles. So suppose R is an integer from 1 to n minus 2. And now let's choose T, symmetric matrix of size R in rational numbers, which is semi-positive definite. Suppose it's a full rank for simplicity. And also choose an R tuple of elements in a discriminant group. Now let ZT gamma prime be an irreducible component in ZT gamma, the spatial cycle determined by T and gamma, then we can find a constant C such that degree of irrationality of this irreducible of this component is bounded by C times the determinant of T to this power 1 plus m over 2. Okay, so here's a sketch of the proof. So this this follows basically from some more deep observations about the Bailey-Fourier compactification. So the components of the boundary components in this Bailey-Fourier compactification, they correspond to orbits of the isotropic subspaces E in this lattice N tensor by Q. Okay, that the orbit is under the monodromy group. And because here the lattice M has signature M2, and remember, we are talking about isotropic subspaces over Q, so in particular over R. So in this case, E will be at most two-dimensional. Okay, at most two-dimensional. So the complements are all one-dimensional. So this allows you to identify using a localization sequence for Chell groups that the Chell group of codimension R on period space N is isomorphic to the Chell group codimension R on the compactification. And this allows you to, so first of all, you need to, you take the line bundle L defined before, you extend it to the compactification. And it's well known that this is ample. So let's just fix some K so that this is very ample. So this gives you some projected embedding. Then you can define a homomorphism, the degree function, like in the Hickner divisor case. And you take a cycle to its compactification, to a degree of its compactification under this very ample divisor. Okay, so we have this homomorphism. So you can safely, because this is homomorphism, you can safely evaluate this degree function at the previously given modular form. So you get a modular form with coefficients, not just in spatial cycles, but integers. And then you can use the previous estimates about coefficients of modular forms to obtain this estimates on the degree of irrationality. Okay, everything is similar to the Hickner divisor case. So later on in our application, the lattice, it will have the signature of the lattice will be 26 and 2. So n here is 26 in our case. So this will, like 1 plus n over 2 will be 14. And this is how the 14 in our main theorem is formed. Okay. So remember, our goal is to estimate the irrationality of the modular space of K3 surfaces in a uniform way. So I just give you an estimate on the irrationality of spatial cycles. Now I want to tell you how to realize the moduli space of K3 as the spatial cycles. So first of all, if you fix a polarized K3 surface SL and you consider its primitive lattice, and here I want to twist it by -1. So this will be a lattice of signature 19,2, and this guy as a lattice is isomorphic to this guy. Okay. Two copies of VA lattice times 2 copies of hyperbolic lattice times a rank 1 lattice. Now, the rank sum is the rank 1 lattice. Okay, sorry about that. Yeah, so in the following, I will denote this lattice by capital lambda D. And due to Nick cooling, this lattice emits an embedding into an even unimodular lattice of signature 26,2. Okay, so which in this talk is denoted by this lambda sharp. It's just 3 copies of EA lattice, sum with 2 copies of the hyperbolic lattice. Okay, we have this embedding, and this embedding can be made very explicit. It's not unique, and it can be made very explicit. For example, you can choose the lattice. You can choose an embedding that identifies, for example, the 2 copies of EA in both lattices, and also 2 copies of the hyperbolic lattice, and then choose some embedding of the rank 1 ZD part into the remaining copy of EA. And there are many different ways here. And this is also by Nikuli. So first, I think it's trivial that if you have such kind of embedding, then you have an injection between their period domains. Okay, and it's not so trivial that you can also extend the elements in the modular group, okay, to elements of modular group to lambda sharp. So you can simply here this injection is induced by simply extending, and remember elements in this gamma lambda d, they are the group, they are the automorphisms on lambda d. You extend it to lambda sharp by defining the larger one, by extending it as the identity on the orthogonal complement. So that's how this embedding is defined. So with these two injections, you can get a morphism. Okay, these two injections give you a morphism on the period spaces. Yeah, so from period space, PD associated to lambda d, to the period space of lambda sharp. Okay, so this guy is going to will be finite onto its image. Okay, so here's a proposition. So we're able to realize these images of these periods. They are all components of the Kudlas spatial cycle, ZT0 for sun T. And here the determinant of T will be D over 2 to the 7. And notice that here, the cycle is ZT0. Here we have a 0 there because our lattice, the larger lattice lambda sharp, it's unimodular. It's 3 copies of EA and some with 2 copies of U hyperbolic lattice. So it's unimodular. So in particular, its discriminant group is going to be trivial. So yeah, there's only a 0 element there. That's why we have a 0 there. Okay, so to see how this proposition is proved, let's choose a 7 tuple, omega 1, W1 to W7, in where each Wi is an element, is a vector in the lambda, in the larger lattice lambda sharp. Okay, so that choose such kind of 7 tuple such that their span is the orthogonal complement of the embedding of lambda d in this lambda sharp. And then we can define T as the moment matrix of this chosen 7 tuple W, the moment matrix. And then you can compute the determinant of T in this way. Okay, so yeah, so it's a discriminant of this orthogonal complement, and then it will be the same as the discriminant group. It will be the same as the discriminant group of lambda d up to a sign, and the sign is determined by the ambient lattice, and then this discriminant will be d. Okay, yeah, so we have this. So this proposition basically follows from these two facts. We get those using the definition of a cycle, and we can do this very explicit computation. So yeah, so in particular, the determinant of the matrix data T is D over 2 to the 7. Okay, so but there's a problem here. So remember, we want to estimate the degree of irrationality of the moduli of K3 surface, and from the theoretic theorem of K3 surface, it's the same as estimating the degree of irrationality of these PDs here. This is due to theoretic. So here, what we can do is to realize the image of these periods using this morphism as spatial cycles in this P sharp. Yeah, so in particular, we are able, so because there are spatial cycles and these cycles from some kind of modular forms, and we also have estimate about degrees of these coefficients of these cycles. So we are able to estimate the degree of irrationality of these images, this FD evaluated at PD. But how do we get the estimate about PD themselves? So this is because this morphism, so this is a finite morphism, the degree of this morphism can be controlled. Okay, So it turns out that the degree of this morphism will be the same as the number of Fourier-Mukai partners of a general K3 surface of degree D. Okay, and which is by what we saw is the same as this number is 2 to the omega of d over 2 minus 1. Here, omega d over 2 is a number of distinct prime factors of d over 2. Okay, we have this. So this is actually not hard to see from the construction of FD. So this basically tells that if you have two K3 surfaces in PD, such that they are mapped to the same point in P sharp, then you are able to construct an isomorphism between their primitive lattices, which preserve also the Hodge structure. Yeah, so this is basically the idea of this lemma. Yeah, and this lemma is proved by Orr and Skorobogo-Tov in 2018. And actually, the construction about realizing the period of K3 as special case cycles is motivated by their paper. So many of construction there motivate our construction. Although their paper are talking about things in the context of Shimura varieties, but here we don't need that. Okay, and so we need also to estimate these degrees of this map FD. So here's a number theory fact. So for every positive integer n, this 2 to omega n, to 2 to omega evaluated n, it's bounded by the number of positive divisors of n. And it turns out this guy grows very slowly with respect to n. It's bounded by in a scale of n to epsilon for all real number epsilon, positive real number epsilon. It grows very slowly. And this epsilon is also the epsilon. It also appears as epsilon in our main theory. Okay, so now we are ready to get a uniform estimate. So for every epsilon, we can find the uniform estimate tells us that for every epsilon, we can find a constant such that the irrationality of FD is bounded by C is constant times D to the 14 plus this epsilon. So this basically follows from the information given in the previous slides. So first we have these maps. The first map is the one open immersion given by Torelli, and then we have this map FD, and we also have this estimate of the FD, the image of the PD under FD. There's CUDA spatial cycles, so we can estimate the irrationality using the estimate about coefficients of modular form in this way. So we get, in particular, some constant times d to the 14th power, and combine this with our previous estimate about degree of FD, we get the epsilon there. Okay, so this is my last slide, and thank you very much for your attention.
Okay, thank you very much for the talk. So, any questions?
So is the lattice lambda sharp the smallest lattice in which you can embed all the lambda d? So smallest in the sense of rank, and among
I think so. Yeah. So you need, for example, like this lambda sharp has signature 26(2), and lambda d has signature 920, 18 or 19. I forgot. Sorry. Yeah, you need 19. Yeah, you need their like difference is like divisible by 7 or 8 or something, and that's the smallest possible one that we can choose.
Oh, thank you very much.
And do you know examples of very small irrationalities? For example, like double carbon over project space.
For various examples of small irrationality, sorry, can you say again your question?
Yeah, so do you have any specific examples of a modular space with very small irrationalities?
We don't really know actually. Yeah, we don't really know. And yeah, and let me also mention that, as you can see from this talk, this estimate, although give you the behavior of the growing, but we don't know what the polynomial really is. I mean, there are a lot of space to improve. So yeah, we don't know. Yeah.
Okay, thank you.
So do you have a lower bound?
Lower bound is also a problem. So we are thinking about lower bound, but there are many difficulties here. For example, like one difficulty, it occurs. So we are able, for example, in the spatial cubic fourfold case, we can say, oh, component, the moduli of spatial cubic fourfold, they appear as component of the Higgs divisors, but we don't know how, like if they are just equal to each other or not. So we only have inequality there. And we also have no way to bound those things from below. Yeah.
Okay, so for the lower bound, if it exists, so do you expect it's still a polynomial in D or?
Can you say again?
So the lower bound, so do you think it should be polynomial in D? Or there's some strange constant?
I think I don't really know, but my feeling is it should be some polynomial. Yeah, but I'm not really sure.
Okay, so for the upper bound, so the 14, you think it's not optimal? Or?
We don't really know if it is optimal. Yeah,
Okay.
that's the thing.
Okay. I don't know if you have many examples for FD. When D goes higher, you have explicit number of this irrationality. Or it's harder to compute even for given D.
Say if there are examples.
Yeah. Can you compute explicitly this irrationality of FD?
Not really. So another problem here is we estimate this irrationality by using degree. So so degree can only, so if you have a variety of certain degree in projective space, then you can do projectivization. You can use projectivization from linear space to produce a finite cover of this space to some projective space, and this give you an example in the definition of degree of irrationality. So this tells you that you are able to bound from above of the degree of irrationality. We use this fact a lot. So, and this fact cannot tell us anything about lower bound. Yeah, so, and also cannot tell us about the optimalness. Yeah, so that's a problem.
Okay, thank you.
Okay, so any other question?
You have so generating vector value generating function in terms of classes of a Higgs divisor. And is it possible to find other specialization to classical modular form so that you get also other, so upper bound, similar upper bound for other so discrete invariant of
you say, sorry, I don't quite get the whole picture about your question. So
so basically, the approach that you show that you have upper bound for the irrationality is that
yes.
you start from vector value, so modular form. So with in terms of classes of Higgs divisor.
Yes.
Yes, and then you take the product So you take intersection product with hyperplane section, and then you
in
classical.
Sort of, yes.
Classical modular form. And then so my question is just, is it possible, yeah, are there other specialization to, yes, to do some classical, other classical modular form?
Specialization. Depends on how, what do you mean by specialization?
Maybe just.
Okay, so let me say this. So because I'm not sure because the like in a CUDA special cycle case and Higgs divisor case, they are already modular forms at the level of cycles. So no matter how you like specialize in some sense or like evaluate them, any case, you still get the same kind of modular forms. Yeah.
But the coefficient might represent other discrete invariants of your.
It's possible. Yeah, depending on how you define the homomorphism. Yeah. But I'm not sure if there's other interesting examples there. Yeah, right now, I'm not sure.
Thank you very much.
Okay, yeah. So let's thank the speaker again, and then our next talk will start in 10 minutes. Let's take a 10 minutes break.